A single drop can damage what an entire machine worked to harvest. In California, an onion harvester can lift, shake, and transfer crops across roughly 10 to 15 acres in a day. A manual worker may cover only 1 to 2 acres in the same time. But speed creates a new problem. Run the lifting web too slowly, and onions pile up with soil and dry leaves. Run the conveyor too fast, and thousands of bulbs hit each transfer point harder than necessary. That is why one machine cannot complete the job alone. The crop must be lifted, dried, collected, inspected, and moved without breaking the flow. Today, we are opening up the hidden system that protects millions of onions while massive machines keep the harvest moving. A digging blade slides beneath the crop. A vibrating web lifts the bulbs, and loose soil falls straight back to the field. This harvester can cover about 10 to 15 acres in one day. A manual worker may handle only 1 to 2 acres over the same period. But faster harvesting creates a tougher job. Wet soil adds weight. Crowded conveyors crush the flow. And one poorly controlled drop can bruise thousands of onions before they reach the truck. No single machine can finish this work. The crop must be loosened, lifted, dried, collected, inspected, and transferred at carefully matched speeds. Across California, those small adjustments decide whether hundreds of thousands of pounds move cleanly or return for extra handling. Now watch how each machine protects the crop while keeping the harvest moving. Now watch how each machine protects the crop while keeping the harvest moving. The first number people notice is 10 to 15 acres per day. That figure matters, but it only describes what the harvester can cover while moving through the field. It does not tell you how many pounds reach the next step without waiting. A harvester may lift onions faster than the picker can collect them. The crop builds up in longer windrows, while the next machine works at its own pace. A picker may cover about 15 to 20 acres per day, but that number still depends on dry onions, available trucks, empty bins, and space at the receiving area. Speed at one point cannot fix a delay at the next. Look at the handoff. The harvester lifts the bulbs, removes part of the soil, and leaves the crop ready for drying. The windrower arranges the onions into even rows. The picker returns later, removes loose leaves and dirt, and sends the crop into a truck or large container. If the truck arrives late, the picker slows down. If every container is full, the picker stops. If the receiving area cannot unload the next truck, the delay moves back toward the field. This is where extra capacity becomes extra waiting. A larger harvester may produce a heavier flow, but final output will not rise unless transport, unloading, sorting, and packing can accept it. The crop may sit longer in temporary storage, and workers may move the same bins twice. Trucks may wait with no place to unload. The packing line may run below capacity because onions arrive in uneven bursts instead of a steady stream. So, is the faster machine always better? No. The slowest handoff sets the pace for everything connected to it. A useful daily figure is not just acres covered by the harvester. It is the number of saleable pounds that pass from the field through transport, receiving, sorting, and packing during one operating hour, without forming a queue or returning for extra handling. That figure exposes lost time that acre-per-day numbers hide. Sometimes the answer is a faster picker. Sometimes it is one more truck, a quicker unloading point, more empty bins, or better timing between the field and packing line. The goal is not to make every machine run at maximum speed. The goal is to keep each handoff ready for the next load. But the first delay does not always begin after the onions leave the ground. Machine performance may already be decided months earlier, when the field is planted, watered, and prepared for harvest. Machine performance may already be decided months earlier, when the field is planted, watered, and prepared for harvest. A harvester works best when every row gives it the same job. In California onion fields, seed may be placed about 0.25 inch deep, with roughly 2 to 4 inches between plants and 12 to 18 inches between rows. Those numbers do more than organize plant growth. They give the digging blade a predictable path beneath the bulbs. When onions sit at similar depths, the operator can hold a steady cutting position instead of correcting the machine every few yards. The seeder may cover about 10 to 15 acres per day, but its real contribution appears months later. Straight rows reduce steering corrections. Consistent spacing also helps the lifting web receive a more even flow of soil, leaves, and bulbs. Now look beneath the surface. Drip irrigation delivers water close to the roots, but moisture also changes how the ground reacts when steel enters it. Soil that is too wet can cling to the onions in heavy slabs. More dirt reaches the lifting web. The separating section carries extra weight, and the crop may move through the machine in uneven surges. Ground that becomes too dry creates the opposite problem. Hard soil takes more force to penetrate, and compact clods can travel upward with the bulbs instead of falling through the web. The harvester has to work between those two conditions. The blade must pass beneath the crop. The soil must break apart. The onions must remain close enough to the surface for lifting, but deep enough to complete normal growth. Crop maturity also matters. If the tops and necks are not ready, the following drying and collecting steps cannot run on schedule. This is why the same harvester may move smoothly across one field and struggle in the next. Uneven rows force more steering. Changing bulb depth requires repeated blade adjustments. Wet patches send heavy loads onto the conveyor, while dry sections may produce hard clods and sharper impacts. The operator can respond by slowing down. The digging depth can be raised or lowered. The shaking action can be adjusted to release more soil. But every correction costs time, and every unstable load makes the next transfer harder to control. Acre per day figures do not show this difference. Two machines may cover the same 10 acres, while one carries far more soil, requires more depth changes, and delivers a less even stream of onions onto the belt. A better result is visible in steadier operation. Watch the load entering the machine. Check how much soil remains with the crop. Count how often the operator changes depth. Then look at the onions crossing the conveyor. A smooth, evenly spread flow means the field has already done part of the machine's work. The next challenge begins after the bulbs leave the ground. From that moment forward, every lift, slide, turn, and drop can protect their value or quietly reduce it. From that moment forward, every lift, slide, turn, and drop can protect their value or quietly reduce it. An onion harvester does more than move bulbs from one place to another. The digging blade releases them, the lifting web raises them, and the shaking section drops loose soil back onto the field. Each contact adds force. A bulb may be lifted once, rolled across a belt, redirected at a transfer point, and dropped into a new layer of onions. One small impact may leave no visible mark. Several impacts in a row can press the outer scales, bruise the flesh, or create damage that appears later during storage. Three details control most of that contact. The first is drop height. The second is the speed difference between one conveyor and the next. The third is the surface receiving the crop. A short drop onto a moving bed of onions is different from a harder landing onto an empty steel area. The machine can keep the same daily capacity while reducing unnecessary impact. Watch the transfer between two belts. If the first belt moves faster than the second, bulbs crowd together at the handoff. Soil and dry leaves collect in the same space, increasing weight and pressure. If the second belt runs much faster, the onions are pulled apart and accelerated. They reach the next drop with more speed, creating extra rolling and sharper contact. The cleanest flow appears when both belts pass the crop forward at closely matched speeds. The onions remain spread across the working width, instead of forming a pile or a thin, unstable stream. This is why maximum belt speed is not the target. Controlled transfer is. Some modern harvesters allow separate belt adjustments so the operator can match conveyor movement to crop volume and field conditions. The useful result is visible without reading a display. Bulbs enter evenly, soil falls through, and the next belt receives a steady load. But the machine still cannot collect the crop immediately. After lifting, the onions may remain in the field for roughly 1 to 2 weeks. That waiting period is part of the job. The outer scales need to dry. The neck must lose moisture and close. Loose soil and remaining leaves become easier to separate. A picker arriving too early may handle a crop that is still soft, damp, and poorly prepared for storage. More speed cannot correct that condition. The windrower helps by arranging the onions into clean rows where air can move around them. It does not finish the harvest. It prepares the crop for the next pass. Once the outer layers are dry, the onion picker lifts those rows, removes loose material, and transfers the bulbs into a truck or large container. This creates 4 clear crop conditions. First, the bulb is still held in the soil. Next, the harvester releases it and places it above ground. Then drying changes the surface and neck. Finally, the picker collects the crop and delivers it for transport. Each machine performs one change that the previous machine cannot complete safely. The harvester can cover about 10 to 15 acres per day. The picker may cover about 15 to 20 acres per day. Those numbers matter, but they do not reveal how gently the onions traveled between the first cut and the final container. A better inspection asks practical questions. How many times did the crop fall? How large was each speed difference? How often did the onions change direction? Did they remain evenly spread across the belt? How much product required extra handling? At full field scale, that difference affects storage life, packing yield, and the number of bulbs that can enter a higher value grade instead of being redirected or discarded. That makes gentle handling a direct production decision. The strongest harvest is not only the one that clears more acres. It is the one that delivers more saleable onions after every lift, transfer, drying period, and collection pass. Once the truck reaches the packing facility, physical contact is no longer the only concern. The next machines must turn color, shape, spacing, and hidden defects into reliable sorting decisions. The next machines must turn color, shape, spacing, and hidden defects into reliable sorting decisions. An optical sorter does not inspect an onion the way a worker does. It records signals. A color camera measures visible differences across the surface. Other equipment may use near-infrared light to capture responses beyond ordinary color, while software records size, shape, and position on the conveyor. But a better camera does not automatically create a better decision. The onion must first be presented correctly. Each bulb needs enough space around it. The lighting must remain stable. The belt or background must provide clear contrast. The surface being inspected must stay inside the camera's viewing area. Remove one of those conditions, and the reading can change. Two onions touching each other may appear as one larger object. A damaged area can remain hidden beneath another bulb. Dust or onion skin on the belt can create an unwanted signal. A dirty lamp cover can make one production shift look different from the next. Look at the spacing before the camera. When onions enter in a single separated stream, the sorter can assign one position and one decision to each bulb. When they overlap, the machine receives incomplete information. The camera may be working correctly while the result is still wrong. Commercial equipment, such as the Tomra 3A, shows how color and near-infrared inspection can be used for agricultural products. That is an industry example, not confirmation of the exact machine shown here. Its published performance figures cannot be transferred to another packing line without knowing the model, crop condition, belt setup, and sorting program. The decision also involves more than the sensor. First, the camera captures a signal. Next, the software compares that signal with the selected quality limits. Then a rejection device, air jet, or diverter sends the onion into the assigned path. A worker still checks what happens after that decision. This human role becomes more important when the equipment is perfectly consistent. A misaligned camera can repeat the same error thousands of times. A dirty light can weaken every reading in the same area. An incorrect threshold can reject acceptable onions or allow damaged ones to continue. Consistency is valuable only when the settings and input conditions are correct. That is why workers inspect sample onions, clean viewing areas, watch the rejected stream, and compare results during production. They are not repeating every decision made by the sorter. They are checking whether the machine is still making the right type of decision. Rejected onions also require another question. Are they unsafe, or do they simply fall outside the size, shape, or appearance required for retail bags? Some may be suitable for peeling, cutting, or another processing route. Others may contain damage that removes them from food production. The supplied transcript does not identify the destination of every rejected onion, so that result cannot be stated as a fixed recovery rate. Sorting performance therefore cannot be judged only by belt speed. The packing facility must also watch how many acceptable onions are rejected, how many defects pass through, and how often the line stops for cleaning or checking. Product sent through a second inspection adds labor and handling. Incorrect rejection removes saleable weight from the main line. A missed defect can reduce the quality of an entire finished bag. The best result is a stable stream of separated onions, clean lighting, clear contrast, and workers verifying the output. Once those decisions are complete, the crop divides into two final paths. Some onions remain whole for packing and storage. Others are peeled, cut, treated, and frozen. And reaching -18 degrees Celsius is only part of that job. After sorting, the onions divide into two final routes. Whole bulbs continue toward inspection, bagging, palletizing, storage, and shipment. Their value still depends on work completed much earlier. The outer scales must be dry, the neck must be closed. Mechanical damage must remain low enough for storage and transport. A clean appearance alone cannot repair bruising created during harvesting. Once approved, the onions enter bags or larger packages. Those packages are sealed, placed onto pallets, and prepared for refrigerated or dry storage according to the product requirement. The second route changes the onion completely. Bulbs are cleaned, peeled, cut, blanched, and sent toward individual quick freezing. The final temperature may reach -18 degrees Celsius or lower, but that number does not reveal how quickly or evenly the product froze. 2 onion pieces can finish at the same temperature and still receive very different treatment. A thin piece exposes more surface area relative to its volume. Cold air can remove heat from it faster than from a thick piece. A crowded belt creates another difference. When pieces overlap, the cold airflow cannot reach every surface equally. The exposed product cools first, while the covered area may require more time to pass through the freezing zone. Air movement also matters. The freezer must carry heat away from the product surface, while colder temperatures move toward the center. Before ice formation is complete, the equipment must remove both normal heat and the heat released while water inside the onion changes state. That is why a temperature reading at the exit cannot describe the entire freezing process. ASHRAE guidance on food freezing treats product thickness, heat transfer, airflow, and freezing time as connected variables. It does not provide one universal setting for every onion line. The correct operating conditions still depend on cut size, belt loading, equipment design, and the required final product. Energy use creates another test. A conveyor, pump, or freezer fan may not face the same load during every operating hour. When fewer pounds enter the line, running every motor at one fixed speed may use more power than the production demand requires. A variable frequency drive can adjust motor speed where the equipment and process allow it. The United States Department of Energy describes variable speed control as a practical option for matching some motor-driven equipment to changing demand. But slower is not automatically better. Reduce freezer airflow too far, and heat removal may weaken. Slow a conveyor too much, and onion pieces can accumulate or remain in the wrong position. The useful question is not whether the motor can run more slowly. It is whether each pound receives the required airflow, movement, and treatment without unnecessary energy use. Now return to the first machine in the field. The harvester could cover 10 to 15 acres in one day. That number looked like the clearest proof of performance. By the end of the operation, it is only one part of the result. The field had to present evenly spaced onions. The digging blade had to release them without carrying excessive soil. Every conveyor had to control drops and speed differences. The curing period had to prepare the outer scales and neck. The optical sorter needed separated onions, clean lighting, and reliable settings. The freezing route needed controlled airflow, product spacing, and enough time to remove heat. A better final calculation therefore combines 4 results. How many saleable pounds leave the facility during each operating hour? How much energy is used for each pound? How many times must the product be handled or inspected again? How much of the crop remains in the intended quality grade? These questions do not replace every technical measurement. They reveal whether speed created real value or merely moved problems farther down the line. The same question extends beyond one California harvest season. A fast operation must also be judged by how it uses soil, water, labor, storage, and energy over repeated years. The remarkable achievement is not how many acres one machine can cross. It is how dozens of small decisions, from planting depth and conveyor speed to sensor lighting and freezer airflow, must remain correct so every pound leaves with the highest usable value.